this is a line of work that we started in 2019, and a lot of it has been spearheaded by Dylan Foster. Some later results are due to Fan Chen, who is a PhD student with me, and Kostas Daskalakis. So let me motivate the problem. And there's a course that Dylan and I developed on this subject called this statistical decision making and reinforcement learning. There are lecture notes and course notes, and this will be updated in a month or two with the new results. Okay. Need to focus. Okay. All right. So I would like to study the following interaction between an agent or a user and the environment. At every time step, the person, decision maker, receives some context xt, makes a decision pi t, and observes some kind of reward, the quality of the decision, and auxiliary observation about the decision. Okay, this is the very generic interaction protocol, and this goes on for capital T rounds. So little t is the current time step t, and everything is causal, so you only know what happened in the past. You can think of a doctor observing a string of patients. That's an example you can keep in mind. So xt is what the doctor knows about the patient, medical history, current symptoms. The doctor makes a prescription treatment strategy, and then observes at some point how good the prescription was. And maybe there is some auxiliary observation that will become later important in the talk. But you can think of observation as maybe disease progression, something that can help make the next decisions better and better, right? So it's not just about the reward necessarily, although in the beginning of the talk we'll consider just the rewards. Okay, this is a very general problem. If you're in advertisement, it's the same problem, except that you have a user coming to the website, and you know something about the user. You make decisions about the products to recommend and so forth. And more recently, this is also a problem of interacting with, say, ChatGPT, where the context is the query or the question that the user sends to ChatGPT, enters in ChatGPT. The system needs to make a decision, which is a string of tokens, which is the output. It's a very complicated decision. And of course, the reward is some kind of, whether it's a correct solution to the problem, let's say, if it's a math problem. All right, so, this is a very general formulation, and what I would like to keep in mind is that this decision pi t can be a very highly structured variable. It's not just a finite set of decisions, but has some structure and potentially continuous and so forth, right? The question is, how do we model this problem? In particular, this problem subsumes what's called episodic RL, because at each time step, my decision is to deploy the robot for an episode with a particular policy. So pi t itself is a policy of what to do in every situation. Robot comes back, we update the policy and observe how much reward was collected. For a doctor, pi t again can be a whole decision tree of what to do at every time step. If the temperature is still high, if fever is still high, then do this and so forth. Right? So pi t is a structured object. You can think, if you like pictures, you can keep this in mind, this picture. So there is a kind of a two-dimensional space of context and decision, and the y-axis is the reward. And so at time t, there is some ground truth that we'll assume. This is the curve here is the surface is the true reward, or mean reward, as we will see. Mean reward for every decision in every context, right? It exists, we don't know it, but this is how we're going to be modeling the problem, right? So in some contexts, some decisions are good. If it's a ChatGPT and context is a question for like a math question, then the decision can have a 0-1 surface, whether it's correct or not, right? So that would be like a very complicated 0-1 surface. Okay, and so at every time step, you're put into the slice, right? You know the context, you're put into the slice, and you need to make a decision. And so the decision that you make it elicits some kind of a noisy value of this curve. And the question is, how do you propagate this information to other decisions and to other contexts, right? How do we make this into a kind of a statistical non-parametric problem? All right, so this is what we're planning to do. I'll start with structured bandits, and this is a problem where I remove the context. So let's just forget about the context and think of just that one slice that I showed on the picture. And the protocol is very simple. Decision maker at every round selects a decision pi t. They need to randomize in many cases, and so we'll consider a randomization distribution pt. So pi t is selected from pt. Of course, the way it's written, pt can be chosen. This distribution is chosen based on the past, right, without looking into the future. And the decision maker observes a noisy reward where f star is that function, that surface that I just plotted, right? So it's a f star of the decision pt, and epsilon t is let's say sub-Gaussian noise. And the assumption is, what do we do in statistics or machine learning? We say that we're going to be working with some class of models, let's say neural networks, such that we believe we're going to assume that f star is in this class. So that surface, the true unknown surface that gives us mean rewards, is in the class. It's not crazy to think that there exists a neural network that takes medical history of all these people and current symptoms and spits out how good the decision is for that person. The question is how do we behave in such a way that we quickly find that surface, and maybe we don't actually need the surface itself. Maybe we just need the maximizers of that. Yes.
So here, where is the context in the
yeah.
pi?
So that's what I said. We're going to simplify it for a second. We dropped the context. Yes. We're just looking at that slice, one slice through the problem. Okay. You can have two objectives, or at least two objectives. One is regret. So along the trajectory of our decisions for t rounds, we compare the mean reward that we've obtained to the mean reward of the best action that we don't know, right? Of course, this does not depend on t, so you can take it out, but it's written in this way. This forces the doctor not to be too wild in terms of exploration, because the doctor has to be careful about prescribing things that could elicit very bad regret. In the second version, which we call PAC, you interact with the world for t rounds, and then on the t+1, you output a decision, and you only pay for that decision. So the doctor can kill as many patients as she or he wants, and then, but presumably learn from that experience and then output just the final one. So depending on your application, this or this can be the right measure. And many of the results, even if I state a result in this setting, there is a similar result in this setting, and so forth. And the question here is, from the kind of statistical point of view, is there kind of a Vapning-Chervonenkis-like theory, or the empirical processes are important here or not for this problem? So in other words, if I give you a class F of like neural networks, let's say, or some other functions, how many rounds do I need to get this regret to a certain degree, right? If I normalize by capital T, let's say, in this one, then I would like sublinear or sub-constant, and if I don't normalize, sublinear regret. And so how quickly does that go to zero, depending on some properties of the class? So this problem has not been solved until recently. And more precisely, what I would like to understand is the min-max formulation of the problem, the way we do it in statistics. We look at min over all algorithms, max over the models, the worst point in the class F, of expected regret of the decision maker, right? And the same thing I can write for risk. So I would like to understand By understanding, I mean that we create lower and upper bounds that, we get a lot of satisfaction if they actually match. Right, and these should be properties of the class F, as I just mentioned, potentially properties of the decision space as well. And of course, there should be some rate with T. Okay, so a classical approach to, you recognize this as a multi-arm bandit problem. The only thing that's different in this problem is that the space of decisions is potentially continuous or complicated. I didn't say that this is a finite set. And there is some structure among the arms. In the multi-arm bandit problem, you have unstructured arms. So the mean reward for one arm does not tell you anything about the mean reward for another arm. Here, because we're putting the structure of functions across the decisions, we're imposing some additional information. But if you remove that structure, there is something called optimism that is a basic primitive. And let me just describe it. This is called the multi-arm bandit problem. So there you have A arms, you have an unstructured set of means, let's say sub-Gaussian noise. And a standard algorithm is what's called UCB, upper confidence bound, which says estimate the mean just by averaging, looking at the average reward you've obtained anytime you chose decision pi. Right? These are just the time steps prior to the current time step when you did choose that arm. And you add some kind of confidence bonus. The algorithm is just to choose the largest, the pi that maximizes this value. And somehow what can happen is either the mean is large, so that's good, or you're choosing that arm because the confidence width is large, so you have a lot of uncertainty. And by doing so, you shrink the uncertainty. Right? So this procedure combines exploration and exploitation into one go. Why does this work? Just visually. So suppose I have some decision space pi. I have some estimated mean. So this is what I believe is the mean reward f hat t for every action, right? So then if I can construct confidence bands, the top is UCB, the lower is LCB, then the method says, hopefully they're constructed in such a way that f star, the true function, is always pointwise within the confidence region, within the confidence band. If I choose according to the top of my confidence band, how much regret can I suffer? Well, the optimum is here, but that's less than this point, and that's less than that point. So by doing this, you see that the regret is at most the width of the confidence band at the selected point. So as long as I can ensure that at all the points that I select, the confidence bands get smaller and smaller, this method will work. Unfortunately, this is not possible for complicated classes of functions. It is possible for finite arm bandit, just by pigeonhole principle. You have to choose some arm, and you have to decrease some confidence interval. It is possible for linear bandits. So this is the classical lin UCB algorithm. I'm not even putting the references, but okay, I guess classical, like 10 years ago. Right, there's a linear structure. Pi lives in d-dimensional space, theta lives in d-dimensional space. Both are, let's say, norm bounded. And there's a way to construct the analog of this confidence band. It will succeed. In other words, you do get regret something like square root of dt for this problem. Now the question is optimism the right principle in general for structured bandit? I already said it's, the answer is no. Let's dig into a little bit more of why that happens. And the key here is information versus regret. Suppose your class F has just 3 functions, these different colored functions. We're maximizing. Is this a simple problem or a difficult problem? you know that one of them is correct. One of them is true. You don't know which one. Do you care that you don't know which one is true? No, because they're all maximized at the same point. So this problem is very easy. Right? Whatever the complexity or the VC dimension of this class is, it should be 0 or 1 or constant. Right? There's nothing to do. But imagine you shift them a little bit, shift these functions. All of a sudden, if they're spaced, in kind of in a way that makes it the signal to noise ratio not too large, then you have to spend a lot of time here trying to figure out which one is the true one, because you're getting, let's say, Gaussian rewards. And every time that you didn't understand which one is correct, you have some kind of regret. So this is a difficult problem. So somehow shifts in this direction all of a sudden can create difficulties for the exploration, right? You start seeing that whatever the complexity of this problem is, it cannot be some kind of covering number, right? It has to do something with the maxima, right? We don't care about these parts, right? Maybe we need to cover these parts, something like that, right? It's a little bit subtle. But here's the problem. What if there's an arm that has a very high signal to noise ratio and it's suboptimal? Then first, by choosing this decision, when I say arm, it's the same as pi, decision, action. When I choose this, I get a lot of information about what is the true function. And then I can go to the maximum. This has been a problem for us trying to show lower bounds also for optimization using information theoretic methods, like 15 years ago, because an algorithm can stay away from the minimum because and not go down to the minimum of the function, because higher up it has more information, a higher signal to noise ratio. So how do you force an algorithm to actually go down to the minimum where the signal to noise ratio could be smaller? Anyway, so these are the difficulties. And the point here is that these confidence bound, the optimistic results will fail for this problem. And Thompson sampling will fail for this problem, because it will start focusing on this region and not care about information. This is information, this is optimization. So we need to combine these two. And it's unclear, if I give you a class F, how to understand complexity of this. Okay, and let me do it this way. I will give you some intuition from the multi-term lower bound, from the MAB lower bound construction, for what the complexity could potentially be. The multi-term bandit lower bound says that the minimax rate for multi-term bandits is square root of AT. This is the after T rounds, this is the optimal minimax regret. It is attained by UCB, the upper confidence bound method that I just described. So here's how you show a lower bound. So first of all, this is the set of model, right? So it's A arms, A decisions with mean F, where F is just some vector in 0, 1 to the A. Okay, so this is your noise model. I mean the model. We take a difficult subset, the way we do it in statistics always, right? Take a difficult subset, and I will describe the subset as F1 will be just a delta bump on the first coordinate. The rest is 0, visualizing like this. And every Fj for other j's will be this bump plus another bump at the jth location. But the bump is twice larger. And we'll take the size of the bump to be square root of A over T. This is the level where it's difficult to understand which model is true. And let me just say that an algorithm is specified fully by a sequence of mappings P1 through Pt, where each mapping is conditionally on the history selects the distributions over action, right? So when I refer to an algorithm, it's just a selection of these P's, right? Of course, when histories are random, PTs are random. Okay. So then the lower bound proceeds as follows, or it can be shown as follows. Let me write P sub f as the average profile of my randomization distribution if I deploy my specific algorithm, I fix my algorithm, within the model parameterized by the mean f. Okay, is this object clear? This is my algorithm. It's specified by these random maps. And what I'm doing is I'm deploying this algorithm in the model specified by a little f as the mean. Okay. So that's my average profile in expected, right? Expected average profile. You can easily see that this expected regret, if I normalize by t, is just a kind of a one round shot regret from this distribution just by linearity. Okay, where pi sub f is the optimal action if the true model is f. Okay, so let's think about this lower bound. So what we did is we picked some reference model f hat. Here it's f1. So there's some special f1, and then the rest are confusing fjs, right? Later we'll call it f hat. Then we fix an algorithm and compute the average profile of that of those actions under that the fixed model. Then we find the worst case nearby alternative by solving argmax of this regret. So it's the most confusing of the fjs, the one that elicits the most regret when the algorithm thinks that the true model is f hat. So the algorithm thinks that f1 is correct, statistically cannot distinguish it from any fjs, and that we're picking fj to be the worst one, the worst alternative. Okay. So just stepping back in statistics, when we want to show lower bounds, we have our set of models, and for the 2-point method, we pick 2 models. They're statistically hard to distinguish, but our inability to distinguish them implies a loss in our performance, right? Here, the algorithm is interactive. It gets data, updates, gets data, updates. So the alternative is selected based on the algorithm. It's very important. We first fix the reference model, then fix the algorithm, and then the alternative, the second point for the lower bound, is selected based on these two, right? Different from what we do in statistics, like in the classical non-interactive statistics. Is this clear? Was this clear? Okay, good. Okay, and then there is a change of measure because statistically you cannot distinguish f1 from fj. To go to that worst case alternative, the algorithm pays, in analysis you pay some Hellinger distance or something like that, some information theoretic distance. Okay, so this motivates the following notion of complexity, which will turn out to be the right complexity for decision making in this problem. It is the best distribution I can choose for the worst case alternative, having fixed f hat. So f hat is a reference model. This was f1 in the lower bound construction, but in the upper bound construction, this will be something that we estimate. So once I fix f hat, I'm going to choose the best randomization distribution, such that no matter what the true model is, I pay hopefully small regret. Now, I'm staying in some kind of a neighborhood of f hat. Later, this will become the Hellinger ball. But right now, this is just because I'm thinking of Gaussian rewards, I can just think of squared error, right? And this is importantly, this is under that p, right? So it's a closeness under that p. So the algorithm that we had before here, right? For the lower bound, we don't know where this will land, or where this will land. So for the complexity computation, we might as well just take a minimum over this. So you can think of the lower bound construction in the previous slides as max over f hat, or f1, min over algorithms, max over alternatives, right? That's exactly the two-point construction. Are there any questions about this quantity? It's a one-shot quantity. So if you compare it to the min-max that we want to understand from the global min-max, it was a min over all algorithms, but here it's just a one-shot quantity, so it's not a crazy computation. So we call it DEC, decision estimation coefficient. This is a version of that, and it depends on the class F and the first point F hat, the reference model. And if you take the maximum over the reference models, this is just a complexity of the class F, which I claim to be the right notion of complexity for this very general set of problems, like a VC dimension, let's say. There are technical reasons for including F hat also into the class. For the pack results, you don't actually need to do it, but for regret, it's important to include this F hat. And importantly, this is over a convex hull of F, because the reference model can be indeed in the convex hull of the other models, as we will see. Any questions about this? Yes.
Just a notation question. So pi t is again defined in terms of the p, or?
Yeah. So pi. This is just a complexity. It has nothing to do with an algorithm or right. And my claim is that somehow this is involved. This is both upper and lower bound for that min-max regret. I will also claim that you can get an algorithm out of this. Okay. So any other questions? All right. So our journey kind of started with the Lagrangian version of this problem, where you, instead of constraining, you subtract off that quadratic term. I think this is a Lagrangian version. There are more references now. We've refined and developed these quantities for other settings as well. But yes, so the offset version is just what is the regret that you offset by a scale of gamma of the closeness to the reference model. Think of this as information you get from the decision, and this is the regret of the decision. And here it's saying, what is the best randomization distribution that brings me the least regret while paying no more than epsilon in terms of closeness to the reference F hat. Okay. No questions? Okay, so the paper of Foster, Yanjun Han, and Noah Golovich, and several others in the following years established upper and lower bounds on this min-max regret in terms of this quantity DEC. It's almost matching, except for a term that I did not yet define, SQ. Yes.
So the gamma.
Yes.
The trade-off,
Yeah.
information. So what have?
Yes. So these two quantities, one depends on epsilon, one depends on gamma, and you can go from one to another. In general, this is the right notion the tighter notion. This is always larger than that. Sometimes you can reverse the inequality. So for instance, for pack regrets, for pack results, you can work with this notion and translate gamma to epsilon.
Okay, there's a correspondence.
There's a correspondence. Good, thanks. Yeah, so if you choose epsilon, and there's a similar result for offset under some a little bit clunky assumptions, but this is the cleanest one. The only difference is that the scale at which you evaluate these two DC quantities. Okay, starts to look a little bit like modules of continuity for those who are familiar with Donoghue, and I'll mention the connection as well. Okay, a similar statement can be made for risk for the pack setting with a slightly different notion of DC that I'll define later. Okay, so just like a VC dimension, you can plug in your favorite multi-arm bandit and then see how it behaves. And indeed, for a multi-arm bandit, you get the DC behavior as epsilon times square root of A. For linear bandits, epsilon square root of D. For other parametric classes, like epsilon times square root of the effective dimension. For non-parametric, you get this behavior. You can also have a threshold behavior, where it's zero, non-zero according to the threshold, and you get fast rates from that. So you do recover many of the results, and sometimes the only thing you don't recover is the dependence on the problem parameters, which should be square root of A. That was your question. Yes. So this is a very subtle question that we've spent several years on the gap between this and that, and which one is correct. And the point here is that genetically, I haven't defined this. Genetically, there are situations where this is correct, and genetically when this one is correct. So for instance, in this setting, it should be square root of A, but in this setting, it should be D, not square root of D for the linear bandits. So DC alone cannot distinguish that level of granularity.
Is this key quantity SQ?
Yes, coming next. I will first state the algorithm, keeping the suspense. What is the SQ until just a few more slides. Here's an algorithm that uses the Lagrangian version of that DC, where you offset by this quadratic term. It says, get f hat t as an estimate, that's my current estimate, using something I have not defined, an online estimation algorithm. I'll define it in a few slides. Once you have it, solve this min-max problem. Sometimes it can be solved, sometimes cannot, computationally, but from the statistical purposes, this is a solution. And sample and update the algorithm. Okay? It's a very basic result. The proof in this case is actually one line. So I will just go through this. Regret is equal to that, by definition. We're going to add and subtract the quadratic term. This is upper bounded by that DC complexity at every round, because pi t will have the distribution which solves the min-max, and f star is in the class, and so this is bounded by that DC. There are t of them, so t times DC. And this one is something I need to control. So I'm piggybacking on some secondary procedure, which is an online estimation procedure, that will compute f hat t. Given that f hat t, I can solve the exploration problem. So what is the online regression? Online regression, or denoising of an individual sequence, says, let pi 1 through pi t be an arbitrary sequence, and I'm using the notation that we need. And suppose that I receive reward at these points which are not IID. The claim is that there exists a sequence of estimators. Each f hat t depends on just the past, such that for any sequence pi1 through pi t, the denoising error on that sequence, remember f hat t does not know about pi t, is bounded by that est sq. So what I'm writing here is that est sq, the estimation error, the upper bound on the estimation error. So how many of you know what this algorithm is? The one that gets log cardinality f. Exponential weights. And there is a good understanding of what in general, what kind of complexity you should get for not finite class f. And by the way, this fact is not known to, I think, many statisticians. It's very strange for statisticians because it's a denoising error on an arbitrary sequence, right? It's saying that there is no way to, mess me up too badly when I make these predictions, because I still do observe noisy values of f star. Just this sequence of points is not revealed to me right away. Think of this as a not even fixed design. It could be adaptive design. So the sequence of pi t's can actually depend itself on the past. So it's not even fixed design setting with revelation of the sequence. Okay. Now, if there is no noise, then you can get this log f by what's called the halving algorithm. Just look at kind of who predicts what. If for a finite class, it's the the exponential weights of Wolfk. You can look at this book. In general, I spent 10 years of my life on understanding how to develop these quantities for a general class f. Okay. Does this give us anything interesting in the contextual bandit setting? Now, I claim the fact that now you introduce xt is not very difficult because everything is conditional on xt at round t. So here's the model. You observe, first you observe xt, then you select pi t, and then you observe this reward for some f star in the class. So here is a procedure that was the beginning of this line of work with Dylan. You have f hat t, which is an online regression estimate with respect to these past data. So you have the secondary online estimation procedure. Oh, by the way, maybe I didn't say this clearly. Why can't you use the usual regression, statistical kind of least squares? Why can you not use it? Because the sequence of the pi's, even if x's are IID, the pi's are not IID because pi's depend on everything that we've seen. So there is a dependence, non-trivial dependence introduced by this choice. So you have to use a result that depends on that works for an arbitrary sequence. It's called the individual sequence result. Then you can compute the inverse gap weighting distribution, which turns out to be the closed form solution of that DEC problem, which we did not know in 2020, but we know now. There's a closed form, very simple solution, and you sample and observe reward. And this actually works well in practice. There's no confidence, there's no optimism. It works for any class f, and it's a simple randomization procedure that balances exploration-exploitation. It's part of this Microsoft library. Okay, so let's move to general decision making. We would like to generalize it further, these ideas, and we can generalize it to have almost no structure, in the sense that it will even be weird that you can say anything about this problem. Yes?
I think about your decisions to estimation algorithm as generalizing UCB conceptually in terms of UCB will choose things that have a good, as you put it, a good mean, but also you want to control more, so actually advantages things that have like uncertainty. And in your thing, you have like you choose an action that has good loss, but also this Hellinger under the
there's a Hellinger uncertainty.
Is that anything about conceptually similar or different?
I don't think of it as similar. I think of this as different. And particularly if you look at this solution, there is no confidence estimation somehow in this. There is no proper way of saying confidence. I'm not making any statements, statistical statements at point-wise about the inclusion of F star in that confidence bands, right? I think of this as a different procedure. Now, UCB of course provides upper bounds on the DEC. You can make that formal, but often very loose. Okay, so in general, we have a collection of models M, decision space pi, and observation space O. This is going to be as general as you can make it, probably going back to kind of Wald 1948, but with interactivity now. There is a loss functional that maps a decision and the model into reals, typically positive numbers and non-negative numbers. And we make an assumption that M star is included in this set of models. M star now is a model. What is a model? It's a conditional distribution of observation given decision. In other words, the interaction is even simpler. At every time step, the decision maker makes a decision and observes OT from M star of pi t, right? Almost no structure. How can you make anything here at this level of generality? Again, you can consider regret, which is the cumulative loss of these decisions in M star, and the final one, even simpler than before. Again, min-max formulation, same thing. We want to understand the min-max as a function of this class of models. And what we did in the previous slides is the case where you can get rewards from observations. Observations contain some measure of how good that decision was, some objective value. So it be quantified as existence of some known function that can extract reward out of the observation, and the loss is the difference. But you can have other loss functions, and that's where this bridges to modules of continuity and other settings will come in a second. Okay, so let me just quickly scroll. So multi-term bandit, of course, you can write it this way. Structured bandits, we've already covered. Contextual bandits, you can formalize it in that language. RL, as I mentioned. But in general, you can write down a class of models where there is some non-trivial leakage of information from, let's say, I don't know, like the 10th bit of the observation tells you something about the model, right? The nature of the model. And these are real, right? You can have an RL procedure where, when the robot makes a left turn on the 50th step, it turns out to be important. So you would like that information to propagate, not just the final reward, right? So everything we're going to be doing has to be information theoretic, right? You cannot have just mean rewards. Mean rewards are no longer sufficient statistics because these probability distributions can leak information in some non-trivial ways. Okay, just continuing. Okay, statistical learning. We give out an estimator given past IID data. This is kind of a vacuous decisions that you're not making any decisions. You can subsume statistical estimation or estimation of linear functionals, there's a functional on the space of distributions. Let's say a fine functional, and then your loss function is some function of how well you estimate the real value, the real value of the function. Okay, and for this we know that Donahoe, Liu, and others identified a certain modules of continuity that characterizes the rates here. Okay. Before I get to more details, this whole construction that I just described, you can think of this as a two-point construction, right? It's a hypothesis test, at least for the lower bound, where we fixed the first point, the reference model, then fixed the algorithm, then chose the second point in the worst case manner. It's a two-point method. But we would like to have something that resembles a little bit more like Fano inequality to bring richness of the class into the picture. And this goes towards closing that gap between upper and lower bounds in the scale of the parameter. So consider the following definition. It's a we call fractional cover. Given a space of models, we look at the best way to spread our distribution over decisions, such that for any model we have some non-zero mass given by this randomization distribution on the near optimizers, delta optimizers of L. Okay, it takes a little bit of time to process, but it's another way of understanding complexity of near optimizers of your decisions of your models with respect to the space of decisions. Okay, why is this called a fractional cover? Well, indeed, if the loss is actually a norm, and M is the same as pi, okay, you can have a space of decisions being the same as space of models, then if for instance, if you choose pi m to be a uniform measure on some representatives, that is exactly the notion of a cover. It says how well can I place my epsilon net so that I get at least 1/n coverage on all points, which means that I have an element near any chosen point, right? Because the probability is at least 1/n. Okay, so you can think of this as a relaxation of the usual notion of cover. It's like a continuum notion of a cover. And okay, I mean, some versions of this come up in computer science, theoretical computer science. But it's a useful notion. And we're going to make one assumption, which is strong, or somewhat strong, but that the KL radius is bounded for the class of models. In other words, there is a center M hat such that all other models for any pi, these are conditional distributions of observation given pi, right, are within CKL from that reference. Okay. Under this condition, this paper of Fan Chen and others establishes upper and lower bounds that are exponentially separated. This depends on log fractional cover, but this depends on the fractional cover itself. And this depends on the CKL radius. It cannot be infinity. But it works for arbitrary. There is no more structure. I haven't added any more structure to this problem. So even at this level of generality, when there is interactivity and no more structure, you can already characterize which problems are learnable. In other words, there is a non-trivial guarantee that can be made, or which ones are non-learnable. In particular, this solves an open problem about characterizing multi-term bandit problem. Like which multi-term bandit problems are learnable and which ones are not. This provides a characterization. To note, a fractional cover alone cannot distinguish between this and that, because there exists situation where this is the true, and there exists situation where this is true. Just because there's essentially no assumptions. Okay, now we're going to merge this Fano-like. It's not clear why it's Fano, but it has some kind of notion of complexity, right? Like richness of the class. Fano with the 2-point of the decision coefficient. And now we get something a little bit better. So let me first define the decision estimation coefficient, which I already defined for squared loss, which is just like Gaussian rewards. But in general, for this setting of a class of models. So as before, it's a min over my randomization distribution, max over models. What is the expected loss I can suffer if I use that distribution? Provided that I stay within the Hellinger ball around the M hat. This is the direct analog of my squared error epsilon ball, right? Now it's a Hellinger ball. And the same way we provide a kind of a single complexity, which is for the worst. And the same thing holds. So you for this min-max problem, you can get upper and lower bounds. And again, these two differ in general by this estimation, except now it's estimation in Hellinger distance. Before it was the square, the online regression. Now it's online density estimation with Hellinger distance. Okay. Okay. Just very briefly, what that is being able to control this quantity. So this is like a denoising error on a sequence that is arbitrary, right? And again, this is possible. The method that works is again Wolf exponential weights, because you can go to KL loss, and that gives you ability to work with log loss. And there's a long line of work even before Merhav and Feder about kind of understanding this setting. Okay, so under that condition, with the mild additional assumptions, we can almost get the matching lower and upper bounds, where the lower bounds is a sum of two terms and the upper bound is the product of two terms. But now notice that both are log, and here it's a log. So now they're not exponentially separated. They're still polynomially separated because this is a product and this is a max or a sum. One difference is that this is a convex hull of the set of models, and this is just the set of models. So at least for convex set of models, these match up to, you know, A plus B versus A times B. But again, we used very few assumptions in this structure of this. Okay, so very quickly, a few extensions. There's a notion that I avoided defining for this notion of complexity, for the risk. And that actually involves decoupling the P here and the Q here. So when you take the infimum, it's infimum over P and Q. One is for the final decision and one is for the exploration. Okay, so you can think of this as two choices. And that turns out to be an upper and lower bound with the same caveat for this problem, for the pack problem, where you just output the final T plus one. Okay. Connection to modules of continuity. Again, I mentioned that this is the modules of continuity. It looks very similar. There's a Hellinger ball around some reference M hat. There's a difference of the linear functionals for those who know this work. There's no min, right? There's just the max. There's no min because there is no interactivity here. It's slightly different. But we can view what we're doing as the kind of a interactive analog of Donoghue. In particular, you can generalize some of these results. So if M is convex, that's the case where things are easier, upper and lower bounds match. Non-convex M, people who know lower bounds, you know, appreciate the difficulty of working with a convex versus non-convex set. If both M, if pi is a subset of a norm vector space and there is a map from M to pi M, any linear map or affine map, and the loss is, you know, the norm between these two decisions, then there is an algorithm that achieves the loss is defined. Oh yeah, so the loss is the final loss is given by this DEC quantity. And in particular, it recovers and generalizes the results by Polanski and Wu. But now we work with interactive estimation, and we work with general spaces and so forth. Now, if you know the paper of Polanski and Wu, they have a very nice, interesting trick in upper bounding the min-max. And something that I haven't yet clarified is pretty much all these upper bounds are attained by, okay, two algorithms. Just by two algorithms. So in some sense, the contribution is not just in understanding the complexity of these interactive problems, but also in coming up with algorithmic principles And in particular, this upper bound is attained by exploration by optimization algorithm, EXO, that I will very briefly describe next. I will describe it, actually, let me mention some other things. Once you have this hammer, you can start hitting a lot of things. So one thing that we hit is this differentially private decision-making. It's a setting where you can think of differentially private channels as those that do not change that much when you change the input to the channel. And so there's this line of work on differentially private decision-making where think of this as a maybe an Apple company who wants to deploy a decision on your phone. It chooses that decision, but also it chooses a private channel for your phone. And then the Z is sampled on your phone from the true unknown M star, but you do not want to transmit Z directly. You transmit O through the private channel. Okay, this is a very brief kind of summary, right? This is called local differential privacy. There's a long line of work started by Ducci, Jordan Weinreich, and so forth. And there is a mean estimation and functional estimation and hypothesis testing under these constraints that you have to transmit data through locally differentially private channel. But now this is an example, and there are many more examples that are waiting to be, I guess, analyzed. This is an example of interactive decision making, right? So we can just calculate those quantities with the DC. And if you do that, what falls out is that the Hellinger simplifies to another notion of divergence. This is just by strong data processing inequalities. So this takes form of the Hellinger. And then we can get upper and lower bounds that are essentially the right scaling. This for a finite class of M. They're almost matching. And this recovers many of the results in the literature that are known. You can now study statistical query, SQ dimension, and we've shown that SQ has actually, in that setting, SQ dimension defined by Feldman is actually very related to DEC, and there is a one-to-one translation, and so forth. Okay, this is the EXO algorithm. I probably don't have time to go through it. It's some kind of version of exponential weights, but it's a little bit tricky. And it's motivated by a representation of Hellinger in this variational form. That's why it looks so ugly. But okay, anyway. So these will be updated in a month with more details, but you can get a glimpse now. Thank you.